This is the chapter 33 homework. We went over a fair amount of it in class. People who ask questions, mostly Ellie, thank you, Ellie, ask questions about the ones that were the toughest ones. So I do think that that's helpful and shows that you, at least Ellie, thought about it pretty well. When I have something like this, I've got, but I'm going to go over most of them. So you're asking for the net flux. So here we've got flux into the page, here we've got flux out of the page. Since they're going opposite directions, the net flux is the difference between those. So I take the area of each one multiplied by the field strength of each one and then subtract, because that is the net flux. So that is in units of Webers, which is a Tesla meter squared. So it says 10 centimeter diameter loop, resistance of 0.2 ohms, and you're asked to find the induced current and need to find, but in order to do that, we need to find the induced EMF and then divide by the resistance. So for each of these, it said that the field strength was changing at 0.5 Tesla per second. It just depends on whether it's increasing or decreasing. C is the easiest one because the field is going into the page, but the area of the coil is perpendicular to the page. And so that essentially has no effect. So whether the field strength is changing or not, the flux is not changing because it's continually zero. For A and B, here you have a field going into the page increasing in strength. Here you have a field going out of the page decreasing in strength. So those essentially have the same effect. In order to oppose either of these effects, we need more dots, or we need an induced magnetic field coming out of the page. So to think about that and find the rate of change of flux, I'm going to find the area. So I did that, multiply it by the change in field strength, and the change that equals the change in flux per unit time, and that actually is going to be equal to voltage. So for both A and B, we're going to have an EMF of 0.00392 volts, so that gets us 0.0196 amps, and in both cases this would be directed counterclockwise. So the key is opposing a change. And again, C was 0. Take a look at number 13. We went over this one. So essentially, we've got a 1,000-turn coil of wire. Gave us the radius of that. Well, it probably gave us the diameter, which is a little bit annoying. But, yeah, because it said 0.1 centimeters diameter, or 1 centimeter diameter. So that's 5 millimeters in radius. Had a flux increasing from 0.1 to 0.3 Tesla in 10 milliseconds. So I ended up again figuring out the rate of change of flux there, and that would give us 0.00157 volts. But that's if we had one turn. If we have 1,000 turns, then we would have 1,000 times the induced voltage. For number 14, you've got a loop. There's current going counterclockwise. It's an 8 centimeter by 8 centimeter loop. It's asking, with a resistance of 0.2 ohms, it's asking you to find whether the field strength is increasing and decreasing and at what rate. So if I have a counterclockwise induced current, the induced field would be pointing out of the page, so that would oppose an increase in the flux into the page. So this field strength must be increasing to cause the induced current to be going counterclockwise. And I could just use equals IR to find the voltage. It said there was only one loop, so that's equal to the EMF or voltage over here, and get around 4.7 Tesla per second. For problem 29, I think we went over 31 in class, but for 29 you can see I screwed up a little bit with which problem I was looking at. So this is a 20 centimeter by 20 centimeter square, has a resistance of 0.1 ohms. The magnetic field perpendicular to the loop is B equals 4t minus 2t squared. So this is a calculus-based problem. And so the EMF is the rate of change of flux with respect to time. So it's the field strength with respect to time times area. So if it gave us that the field strength is this, the derivative of that with respect to time would give us this, and that gives me the EMF at those different times when I plug in the specific time values. And so I get 1.6 amps at 0 seconds, 0 amps at 1 second, negative 1.6 amps at 2 seconds. When I take whatever voltage I get here and divide it by the resistance. So I like that. A little bit of calculus, but not too bad. It makes you understand that the voltage depends on the rate of change. So this one was an annoying one. We talked about how we have to use resistivity, which is an earlier chapter, to get the resistance of the wire. I think I did this in class when everyone was here, so I'm not going to talk about this too much, but basically, I should, because that's why I'm doing this. If we have a 100 turn 0.04 meter radius coil, the wire is 0.5 millimeters in diameter, and it's copper wire. So to find the resistance, I need to know the resistivity of copper, so I looked that up in the textbook. Multiplied by the length of the wire divided by the area, the cross-sectional area of the wire. Well, the cross-sectional area is pi r squared. Resistivity I found, the length was 25.1 meters. How did I get that? Well, if it's a 4 centimeter radius coil, then there's 100 loops. That circumference times 100 would give me the total length of the copper wire. So all that gets me 2.17 6 ohms. And now I can find the voltage. So the EMF that's generated when you have this type of copper in this type of coil with this rate of change, to get 2 amps would be 4.352 volts. So I know the resistance of the coil, I know the desired current, so I can find the EMF that would cause that current. And then that's going to equal to the rate of change of field with respect to time times the area of the coil. So that was a bit of an annoying problem. This one I talked about in class with the calculus solution, or the non-calculus solution is down here. The calculus solution is up here. So this example in class, so that's this example in your book, 33.5. Let me see what page that's on, if I can. It's on page 971 in your textbook. Gives you an idea of how to do this. So otherwise I would have been I would have been struggling to do this. But x, we're thinking it was the distance to the closer part of the loop of wire, so this is x plus 0.01 over here. And it gets you the same result as the way that it did in class, the non-calculus way. So when you weights make fun of me for doing things and taking long, that's because I'm showing you steps and because I've got more than one way to do things. Other problems, 43, 47. So this is for an inductor for 43. I didn't give any problems with that because I think it's unlikely that you see it, but I want you to understand how to do this. So it basically has a step-down transformer. So then the number of turns over voltage in the primary is equal to number of turns over voltage in the secondary. So you get 12,500 turns. In an ideal transformer, the power is equal in both the primary and secondary. Transformers in reality are not ideal, but this one is. So the rate at which energy is supplied is the same as you get out. So power is V times I, so we could do that and figure out the current. And so you can see in the higher voltage there's much less current. 47 was a little bit tricky here. It was because this thing had a resistance. A and B were not tricky. Part C was a little tricky, and it's the resistance between the wires, so between this spot and this spot. And that is only a 3 volt potential difference because the total EMF is 4 volts. Well, each of these lengths has the same amount of resistance, so between this spot and this spot would be 1 volt difference, 1 volt difference, 1 volt difference, 1 volt difference. So between this end and this end there should be a 3 volt difference. 50 says a 10 centimeter wide zero resistance slide, and so there's a picture here. This thing's going to the right. It's going at a constant speed. Normally if this were moving to the right, you would get a force opposing that change. So in order to essentially have it move at a constant speed, the magnetic force would go to the left to oppose the change in flux. You need a push or a pull to the right. They would be equal. So to find the force of the push, you need to find the magnetic force. So this is a critical concept. So the magnetic force would be on the length of the wire. So in order to do that, you need to find the current in the wire. In order to find the current in the wire, you need to find the EMF. Well, the EMF is B times L times V. So I work backwards here then. I've got that voltage. The resistance over here is 2 ohms, so that tells me the current in the wire. So now I can use this Fabille formula to figure out the force that you would need to push the wire. So to figure out the power of pulling that wire, force times velocity, there's other ways to figure that out. It's rate of energy change with respect to time, but this would be the easiest way to do this. 3.12 times 10 to the negative fourth watts. So then the part C of this question is asking what's the direction and magnitude of the current. So I kind of already had figured that out, but the induced current is counterclockwise because that would oppose the change in flux. In other words, here we have a decreasing flux out of the page. So to oppose that, we need a current that's going to induce a magnetic field coming out of the page, and that would be a counterclockwise current. And then this was hopefully an interesting thing for you. Down here, the power dissipated in the resistor is the same as the power used to move the wire. And so that is indicate about energy conservation. If the resistance wasn't all at this spot, or there were other things along the way, then the power dissipated in this particular resistor might be less if there were other resistors in the circuit. But because it's the only thing converting electrical energy to something like heat, those two would be the same. For problem 64, I wanted to make sure you saw something like this graph. I think we had that on a couple of the conceptual questions as well. So you're given a current graph, and you're asked to figure out the potential difference versus time graph. And these are milliseconds, by the way. If that wasn't clear to you, your specific numbers might be incorrect. So this is current through a 10 millihenry inductor, something like that. So if you have the current is increasing, that means that the EMF is going to be negative because it is opposing that increase. So that's your formula for an inductor we talked about in class. From 0 to 2 seconds, I look at the slope of this, so that's di dt. And this is where I screwed up, is like I said, I didn't notice that this was milliseconds at first, so that was quite annoying. So it ends up getting me negative 10 volts here, 0 volts in the region where there is no change in current. And then down here we have a much steeper graph, so much greater change in current, so much greater voltage generated by that inductor, so plus 20 volts. So in this particular case, the big idea is we only get an induced EMF from an inductor when we have a current changing. And remember, if it says through an inductor, the inductor is a loop. So there is an effective area there. It didn't tell you that, but that goes into the strength of the inductor. 77, I asked you to do A and B, or pardon me, A and C. So the initial current going through this would be V battery divided by the resistance, or pardon me, after a long, long time. So if it's been closed for a long, long time, if this inductor has zero resistance, the only thing opposing current flow would be the resistor. Initially, if this was closed, this would have a big opposition to current flowing, and it would be different. It would be significantly different. For letter C down here, it was asking to sketch a current versus time graph from t equals 0 until the current is no longer changing. So you would think if there was no inductor, this would immediately shoot up to V battery over R. But the inductor has a greater opposition initially because the rate of current is changing more rapidly. So we level off and asymptotically go up here to our steady value. Part B was not assigned, but I want you to take a look at this. This deals with Kirchhoff's loop rule, and it helps you think about how you could use calculus to find the expression for the currently at any instant in time. And it says writing your expression in terms of variables, I0, which is the initial current, resistance, and inductance. So I know that the battery voltage is equal to the voltage lost across the resistor and the voltage pushed back by the inductor. And so initially we're going to end up looking, and so all that would equal 0. That's really Kirchhoff's loop rule. of go down through here, through this. So differential equation happens. I wanted to show you a way that that could happen. If you had something like this at an AP exam, they may ask you to set it up. If they ask you to solve it, probably, again, not worth your time. Okay. So hopefully those help you out, and hopefully you understand some of these things better.